This is kind of a work in progress talk. This is kind of an idea that's been, I was at Microsoft Research for about a decade, pivoting to academia. The last couple of years, I've really been thinking about this question of how do we build highly reliable software? And initially I came at this from the view of software reliability is proving some assertion about your code. So I had a really fun opportunity to work with some folks in investment banking about proving arbitrary properties about compliance software that they were building to do reporting for the SEC and stuff like this. So, but there were other conversations I had that were really kind of funny about performance, and so I wanted to share some of these with you guys and my thinking on this. And this comes down to this issue of when I started thinking about performance and compilers, it was, hey, I'm going to have a set of benchmarks like DeCapo or Spec or something. I'm going to run this. I'm going to have JIT warm up. I'm going to discard some outliers, and I'm going to compute a geometric mean. Or I'm going to set up a web service, run some load test on it, and make sure that my response time is less than 100 milliseconds on average. And this is great. This is table stakes, right? Obviously, if your software is just terribly slow, it's no good. But this only gets you so far. This gets you deployed. But then what happens is you see, well, in practice, maybe my software responds in 80 milliseconds on average, but sometimes it's 50 milliseconds and sometimes it's 10 seconds, only 5% of the time or 1% of the time. But at a user waiting 10 seconds, there are people leaving your website. You're leaving money on the table. And so it becomes a big problem of how do I deal with this tail latency, right? And this tail latency performance, this variance, is almost as important as the average case time. And so companies, really spend a lot of time on this. I really like this Tail at Scale by Jeff Dean, from Google, sort of kicked this idea in the mainstream, really like, hey, we have these processes and these tail latencies cost us real money and we really care about them. Now, I didn't like it because it was kind of from a Google perspective about network latency, load balancing, and so it made it seem like a real systems issue. And my question is, no, it's not just a systems problem, right? Like this is not just something that people are going to talk about at AskPlus or whatever. Like this is a software problem. And what do I mean by this? Well, this was a great story I heard from some Node.js people. I'm running a big service, and I'm serving requests, and it's all great. And yes, the triggering cause is there was a network glitch, right? But what then happened and really caused our problems was this network glitch caused us to have some requests pile up. Since these requests usually were short-lived and they got collected in the Gen 0 garbage collection, but now they were long-lived because they were piling up, so they got promoted. That meant we had a long pause for a Gen 1 collection, which caused more things to pile up and more things. So our service just tailed off and died here. And that was the real, the trigger was this network issue, but what killed us was the software, right? And this is one that's network involved, but there's some pure software ones too, like there's some regexes. The regex of Doom was a popular denial of service attack for a while. A simple looking regex this long has an exponential time. People would attack hash tables by causing malicious collisions. And of course, GC, everybody's familiar with janky UI with GCs. So I was like, hey, this is really a software problem as well. It's not just a system problem. And interestingly, like I said, I started thinking about this from a software quality reliability issue. But these problems, like it doesn't matter if my application crashes because I had a null pointer exception, or my application is unreachable because it has terrible tail latency and it has a denial of service attack. Either way, my people can't use it, it's not doing its job, it's unreliable software, right? And so the question is, how do you design a language that solves some of these problems? Like, can we think about this in a bit of a holistic way? Can we eliminate certain features that cause these problems? So let me talk about the kind of the project I've been working on is this Bosky development stack. And the goal here is to, from the ground up, build a programming language and a runtime that's designed to build high reliability, high assurance software. And I kind of take the opposite approach of, hey, I'm going to add a cool new language feature or build a super new clever analysis, because I met a lot of people probably smarter than me that tried those things and they improved the state of the art. But if you look at where the state of the art is today from where you want it to be, it's a huge gap. So I was kind of like, I don't know if I can push that stone up that mountain. So I'm going to take the opposite approach. I'm going to get rid of things that cause me problems when doing program analysis, and interestingly, that cause problems when doing like performance optimization. So one of them is the language is immutable. So there are no reference, you can't mutate values, everything's referentially transparent. You cannot view aliases or mutation or anything in the code. It's semantically invisible. There are no cycles in data structures. Like, seems a little funny, but it turns out to be really useful. One I really like is there are no loops, no iterative loops, and we try and discourage recursion, so we don't want inductive invariance and all that gross stuff. The semantics are designed to be fully deterministic, so that is, of course, no undefined behavior, that's right out, but not even things that are implementation defined or maybe version defined, like what's the enumeration order of keys in a dictionary, right? And this is kind of funny to me, but it's interesting. Over the years, JavaScript specs have gotten more and more prescriptive about the way things are done. If you look back, early JavaScript, it was enumerate keys in any order, it's great, we don't care. And as they've added new features, it's you must enumerate keys in the order that they were inserted in, because developers got really tired about guessing between which version of browser and which, different companies' browsers did it in different orders and having all sorts of weird bugs. So this is another one. And lastly, well, PCRE regular expressions are really weird, so we're going to do a really, regular expression language. And so how does this stack up? So with these features, now can we think about making different choices about how we design a runtime? Oh, and let me show one other thing. Quick question might be is like, wow, that's a really constrictive language, right? Is any developer in their right mind going to get near writing this? And I don't want to go into detail, but in some, no, we're able to connect this nice IR to a fairly friendly surface level semantics for developers. This is Bosky code. Modulo a few keywords, it's actually valid TypeScript code. You have nice block structures, variables that you can reassign, returns, all sorts of good stuff. So if you're a TypeScript developer, you can kind of look at this and be productive, like shockingly quickly. And that was a very nice thing we were able to kind of beat out of it. But anyway, so hopefully that sets up the problem interestingly. We make a couple of design decisions here, which I think are kind of nice. The first one is obvious. Well, we want everything to be deterministic, and there are a lot of things in like a standard library that are not, right? So usually if you look at your standard map or set, it's built with a hash table. And hash tables are really cool because they give you constant insert and lookup time, and they're all great, and they have a slow case where you have to rehash at O of n time. But if you look at these things, if you look at like V8 code, there are all sorts of fun bugs about people like using adversarial values to plop in and cause it to continually rehash, right? And of course that's bad and you can work around this. But no matter what you do, there's going to be some unlucky user that just happens to have the right workload that causes you to do a bunch of rehashing, right? So you get this long tail of variability. And this kind of goes back to this tail at scale paper. Even if you have a very small percentage probability of hitting a slow thing, if you have 10, 15, 20 things that have a slow path, eventually you're going to start hitting a lot of those once you're at scale, right? So the cool thing is we can actually get rid of these. There are actually well-known nice persistent data structures like RBB vectors or using TimSort that give you not just great guarantees on the worst case bound, so you get this omega bound on your worst case, but they're actually n log n, or you can make them effectively constant. So they're not actually that much slower than what was your cool optimized data structure. Plus they have much better variability. We can also get rid of PCREs to get rid of a bunch of these regex problems. And this is great stuff. You don't even, kind of Bosky is nice to do this in, but you could do this anywhere. But where the kind of stuff real fun comes from is when you go in memory management design, right? So what we're going to do is we're going to take an old and kind of simple algorithm. It's a really fun way to think about doing memory management. So I'm going to do a generational collector, and I'm going to have a young space with a bump pointer. And for the old space, I'm just going to use reference counting. This was kind of introduced in 2003, so it's very simple. But if you go in and try and implement this for something like Java, you have a lot of problems, like even though the old space is reference counted, you can't collect cycles with a reference counter, so you need a backup cycle collector. So you're still going to eventually pay some stop the world for the whole heap pods. There are other things like, oh, you can mutate objects. So if you have your application doing a lot of mutation, you're going to have to keep track of these remembered sets, and you're going to have to update all of that. So the cost per collection is not actually just the young space, but it's some application-dependent size on the other thing, right? Well, the cool thing is all these features of Bosky, like, get rid of that. So just by the design, we don't have to have multiples of the heap sort of spare space to make the collector efficient. We just need the space of the memory, which is the young space, and then the old space is ref counted. So we have a constant overhead garbage memory use, right? Since we can't mutate anything, we have a fixed amount of work. So we actually have kind of a real-time collector guarantee here. We're just going to sweep the young heap. We don't need to run a cycle collector. We don't need to do remembered sets. We don't need to do anything, right? So we have a guaranteed real-time garbage collector. The pauses are guaranteed, right? So, and then finally, it's application code independent. Since we don't need to do write barriers, we don't need to do remembered sets, we don't need to keep precise refs on the root, precise root set of anything. So now we can aggressively optimize the runtime as well. So this is really cool. We can do all these neat things, and we don't have to have any sort of complex, clever, crazy machinery. So this is a work in progress, right? Obviously, but this was interesting for me because the focus of the work was, this project was reliability. Like, I want to build high reliability software. But as I said, runtime predictability and consistency are actually part of that reliability. It's actually a holistic thing, right? And a lot of the things that we did to simplify being able to do proofs with an SMT solver actually allowed us to simplify runtime design and be much more aggressive in our optimization. So it's very interesting to see these two things playing together, although oftentimes performance is seen as a complexity thing, but it's really performance is just making your life simple and then doing the obvious thing works shockingly well. So this is, a work in progress. So obviously I proposed some algorithms here. They have very nice theoretical properties, but hopefully I'll be back here next year giving you some black and white benchmarks on these. This was cool, but it also kind of showed that, hey, these properties in this runtime actually open up some other interesting avenues as well, right? So if I know where, if I know that there are no writes to any objects, can I start doing some compiler optimizations much more aggressively than if I had to worry about maintaining a bunch of read-write dependencies, right? Can I do a much more aggressive common sub-expression elimination kind of pass, right? Very interesting things about, like, my code is now fully deterministic. Does that make it a lot easier to think about how doing recovery or migration in a distributed system works? So I thought this was a really exciting demonstration of how these properties enable more than just verification. They enable you to do interesting stuff up and down the runtime stack. And so with that, I think I got a couple references. Like, we are working in GitHub. You can take a look at everything there. Got a little blog going, and if people are interested in this regular expression, we have that as a separate repository as well, actually written in C, so that if other people wanted to try plugging it into some other application, that's a possibility as well. Okay, so I think I wrapped up. I see I have 1 minute to spare, so I have a question or two.
Hi. Interesting idea. I was thinking about if your pause times are proportional to the life set for young generation, how will you ensure that Bosky will scale with applications that require a large heap or have a high allocation rate?
Well, the nice thing is the pause times are basically proportional to the young generation plus the number of old objects that you need that die per generation. But you can batch those into them incrementally. So you can basically guarantee that the application will never outrun the garbage collector, and that the pause time is going to be bounded by the young generation. Now, if you make this like 16 megs or 32 megs, this might start to get a little longer, but this is, of course, maybe a throughput versus latency choice you could make. This is something I hope to explore a little bit more once we have a larger set of code bases to run and do some legit benchmarking. Like right now, the amount of Bosky code out there is not enough to make a really convincing experimental evaluation, right?
Cool, thanks.
Any other questions?
Have there been many situations where the rejection of implementation-defined behavior at the language level has led to kind of needing to use algorithms with worse time or space complexity?
Well, let me put it this way. The asymptotic one is always a bit funny, but I think the RBB vector is an interesting one. So this was, it's basically using a tree for implementing something that looks like a vector in C++, right? So you can do arbitrary insertion and deletion. Now, the interesting thing is the way they do that tree, they argue that it's like you can get like a 4 or 8 gigabyte long list with a max depth of something like 7 or something. So it's effectively constant. Now, that's true in an asymptotic sense, but obviously you're going to do additional pointer dereferences. So you're going to, from a practical standpoint, the cost is going to go up. Now, this is a place where, if you look in that paper, they benchmark, I was using vector and I was using this RBB and I wrote Java code that sort of did a map the way you would in Java, like it iterated index-wise over. Now, the rough part is that means that for every index, it's constant in the C one and it's kind of 7 dereferences constant in the RRB one, which makes it, a 7x slowdown is kind of painful. But the interesting thing is, if you look at the way Bosky works, there are no loops. So this kind of point-wise operation is not possible. What you have to do is use higher order functions. So there's like a map or a filter or a min or a max. And the nice thing there is if you're mapping over this vector, the result vector is going to be the same size as the original vector. So rather than do a point-wise insertion plus the rotations and all that stuff, you can just allocate that memory before running and then just zip over. So that performance delta actually shrinks. So yes, there are places where it is in theory or it is in practice more expensive, but actually the simplicity and ability to understand what the language is going to do allows you to, I think, optimize a lot of that away. Again, this is an area where that's my back of the envelope calculation, but it'll be interesting to see exactly what that delta is when the benchmarks hit the road.
Cool, thanks.
Yeah.